So this idea of area under a curve actually can be used for some real life situations that are not just abstractly the area under some obscure curve. We can use this idea to determine distance if we have information about velocity. So question is, what if we want to estimate the distance driven over a 30-second time interval? This is actually something I've imagined doing a lot, but I've never had the planning to actually try this. When you're driving in a car, you have the speedometer, which is telling you how fast you're going at any moment in time. If somebody were to be recording every 5 seconds what the speedometer says, that could give you a way to estimate how much distance you've traveled in that time. So let's say every 5 seconds, somebody's recording your velocity. So this is what the speedometer is saying at each 5-second interval. Notice this is in miles per hour. So we want to convert it so that we have numbers that are following related units. So we change the miles per hour to feet per second, and that's why we have this new table with these numbers. So what we can do is we can consider a graph where the x-axis is actually the t-axis and the vertical axis is v for velocity. So if I were to plot these, so we have 0, we have 5, 10, 15, 20, 25, and 30, and let's try to give good estimates for the velocity in feet per second. T is in seconds. So let's maybe say that this is 25 and this is 50, and we'll eyeball these points. So we have 0, 25, 5, 31, 10, 35, 10, 35, 15, 43, 20, 47, 25, 45, and then 30, 41. So about like that. So we don't have a formula for a function, but what we do have is we have a way to determine the heights of rectangles that will allow us to estimate what the total distance traveled was. Well, let's see. We have 7 pieces of information, which really should only give us 6 rectangles. So I should erase this last one. Let's calculate the areas of these rectangles and add them up. Now, why are we doing that? Notice that seconds times feet per second is going to give us feet. And we're trying to estimate distance, which is feet. Okay. So these areas, if I do base times height, that's going to give me something whose units are going to be feet. If I do that for each of these rectangles, I'm going to have feet is what the number is going to be. So noticing that delta x here is 5. In other words, the width of each rectangle is the same, it's 5. Let's add up what we get. So we get 5 times 25 plus 5 times 31 plus 5 times 35 plus 5 times 43 plus 5 times 47 plus 5 times 45. And then what do we do with that last rectangle? Well, right now this is a left endpoint estimate. So L6 would be the total of these numbers. We get 1,130 feet if I'm not mistaken in my calculations. Now what about the right endpoint approximation? Well, that's where we're going to use this last rectangle here. That's going to be the 5 times the 41. And notice I'm now missing this leftmost rectangle. So take a moment to calculate the right endpoint approximation of the distance. I got 1210. So think about it, 1,210 feet is maybe a little less than a quarter of a mile, like a little less than a quarter of a mile in 30 seconds. Does that seem reasonable given the speed that they're going? Yeah. So this is an example of how we can use this idea of area under a curve to solve for some sort of physical quantity that's being represented by the area rather than just caring solely about the area under a curve abstractly.